The experiment requires RNA, a reverse transcriptase enzyme, a primer, and DNTPs. The RT experiment is also called first-strand cDNA synthesis. The steps are as follows. RNA is first incubated with a primer at 70 degrees centigrade to denature RNA's secondary structure. This is chilled quickly on ice to let the primer anneal to the RNA. Reverse transcriptase, DNTPs and buffer are added to the reaction. RT reaction is extended at 37 degrees centigrade or higher for 1 hour to allow transcription to occur. RT reaction is heated at 70 degrees C to inactivate the enzyme. The end result is cDNA. There are many reverse transcription kits available that all address different concerns. We are going to cover a few of your choices here. Enzyme choice. For reverse transcriptase, we have several options. A good basic enzyme is MMLV. This enzyme will get the job done, but there are limitations. You can only perform your RT up to 37 degrees centigrade, which can be a problem if you have a GC-rich template or lots of secondary structures to deal with. A better reverse transcriptase is superscript 3. Superscript 3 is a highly thermostable proprietary mutant of MMLV enzyme with reduced RNase H activity. This engineered reverse transcriptase allows the RT reaction to go a higher temperature of 50 degrees C. This means that you get more yield, longer products and greater representation of your input RNA. Can superscript 3 be used for real-time PCR? For real-time PCR application, you may have high and low expressing transcripts in the same sample and you only want to quantify the target of choice. Therefore, you want to have a high sensitivity and specificity as demonstrated with lower CT values and single peak in melting curve analysis. Superscript Vilo contains superscript 3, the same thermostable RT that we've talked about before, but with an optimized buffer mix and helper proteins. It's specifically designed for generating cDNA for real-time applications, thus resulting in high yields and unprecedented linearity across a broad range of sample outputs. The common choice of primer is oligo-DT. It binds to the 3' poly A tail of eukaryotic mRNA transcripts. The limitation with this choice is that you can get a 3' bias of your sample due to where the primer binds. In addition, oligo-DT is not compatible with non-eukaryotic or degraded samples due to the lack of a poly A tail, and hence the oligo-DT primer cannot bind. An alternative is random primers, which are randomized hexamers or non-amers. These primers will bind all along the RNA transcript and so help to overcome issues with secondary structure and give a good representation of the population. Random primers usually result in higher cDNA yields. Some researchers choose to use a blend of both random primers and oligo-DT to get the benefits of both options. The final option for primer choice is gene-specific primers. These will only make cDNA for the one specific target. Gene-specific primers are required for one-step real-time PCR, qRT-PCR reactions. The cDNA yield will be lower with the gene-specific primers since you are only targeting one transcript.